Sino también el más sensitivo del mundo. Su plato esférico colgante, su triángulo que se sostiene de 3 torres por cable, su anillo por donde nosotros entonces movemos nuestros receptores, y el arco que nos da entonces el otro ángulo de azimuto sobre el cielo, nos convierte en uno de los más importantes instrumentos del mundo.
The telescope's 20-acre reflecting dish is 1,000 feet, 305 meters in diameter, and made up of almost 40,000 panels individually adjusted to maintain its spherical shape. 450 feet, 140 meters overhead, a 900-ton platform hangs by cables from 3 concrete towers. Suspended from the triangular platform is a Gregorian reflector system. Since the dish remains stationary, telescope's pointing is done by moving the field up to 20 degrees from a vertical position. The main dish reflects radio waves coming from space and directs them to the Gregorian system. Once detected, the signals are amplified by receivers cooled to near absolute zero, then sent through fiber optic cables to the control room, set in a small building wedged between karst hills at the edge of the dish. In the control room, the signals undergo more transformations as they are filtered, converted from analog to digital, sampled, and stored on the hard drive of the computer. Once the data is stored, scientists use computer programs to make images, prepare maps, analyze their findings, and publish the results. Because of the size and sensitivity of the telescope, radio sources that may require several hours of observations at other radio telescopes can be done here in mere minutes. As the dream of the observatory became reality, scientists from around the world came to Arecibo to see what they could learn through the telescope.
What makes Arecibo Observatory unique among the great observatories in the world is that we do 3 fields of science, and we do it with a precision and sensitivity that's unmatched by any other observatory. Those are astronomy, radio astronomy, planetary astronomy using radar, so it's radar astronomy, as well as upper atmospheric science, and in fact atmospheric science from the surface of the Earth through the outer reaches of space.
Atmospheric scientists study the inner and outer layers of the ionosphere, a region roughly 100 to 800 kilometers from Earth.
We live on the surface of the Earth, and the lower atmosphere is most relevant to our lives. That's what we breathe. If we want to understand global warming, climate change, we need to study the whole atmosphere in order to understand whether our models are making a proper representation of the atmosphere as a whole, and then come back to how that affects us.
The middle atmosphere is studied at the observatory's LIDAR, Light Detection and Ranging Lab. The LIDAR, set on a nearby hill, sends out a narrow, coherent beam of visible laser light into the nighttime skies, and scientists study the returning reflections. Climatology data measured here is helpful in the understanding of natural events such as the movement of Sahara dust, which can cause asthma and other health problems. Planetary astronomers map planets, comets, and asteroids. The Arecibo Observatory radar is also the world's most powerful instrument for identifying and studying the orbits of near-Earth asteroids.
Where one of the very few places on the Earth that can take accurate pictures of asteroids. We can measure very precisely time and speed. So we send out a pulse of radio waves, and very powerful pulse of radio waves bounces off the asteroid or the planet or whatever we're looking at, bounces back, and just before it gets back, we turn off our powerful radar transmitter and turn on a radio receiver and collect the echo. We measure how long it takes that light to get there and back. Then what we usually do is take those images, and in a computer model, we'll make a 3D image like you'd really see if you were there. And this is an example of one of these, what this asteroid would look like from different directions if we were looking at it with our eyes.
Over the years, radar scientists have worked closely with NASA.
For example, about 10 years ago, the SOHO spacecraft had a problem, and they asked us to measure how fast it was spinning. And as I said, Arecibo measures speeds of things. So we said, we can measure how fast it's spinning, because they wanted to know if it still had any fuel left or not. And if it had used all its fuel, it would be spinning very fast. Otherwise, it wouldn't be. So we were able to measure where it was and how fast it was spinning, and answer that question for them. And they discovered that the spacecraft was actually in good health, and they were able to recover it, and it's still taking pictures of the sun today.
Radio astronomers analyze radio waves that arrive from hundreds of millions of light years away, whose signals are far too weak to be detected anywhere else on Earth. Some of the observatory's most important discoveries relate to pulsars, rotating neutron stars that have collapsed into small, dense objects mere kilometers in size.
One unique property of pulsars
Just
is that
about
they're
over.
extremely accurate natural clocks. Pulsars got their name because they're observed as radio lighthouses, essentially. When the first pulsar was discovered in the 1960s in Great Britain, people thought it was a beacon of an extraterrestrial civilization.
In 1974, radio astronomers Joe Taylor and Russell Holtz discovered a binary pulsar and measured the orbital decay of the binary system, confirming Einstein's prediction of the existence of gravitational radiation. For this discovery, Taylor and Holtz received the Nobel Prize for Physics in 1993.
Okay. All right. We'll stop it right here a second, and we'll go into a little bit of history now in the observatory. I can see this button here. Extend, I guess, here. Okay. Now, how do we get that on the other side here? Okay. Okay.
Already set to come back out again.
Okay. Sorry about this. Can't find it. Where's the mouse here? Okay. Do function F8. I can't see it.
Can you?
Oh, you want me to do? You could just do a duplicate, I guess, and I'll do it from there. I'll do it from there. Okay, sorry about that, guys. Not too familiar with this laptop. Well, anyway, thank you again for showing up. And we'll just go through a little history on the observatory. My name is, again, Angel Vasquez. I am the Director of Telescope Operations and RFI and Spectrum Manager. So Arecibo, as we all know, is in Puerto Rico. It's about, as you can see from the map, it's about in the center, top left center, Arecibo in the Caribbean. So that's what it looks like from a satellite. There's our eye to the universe. Arecibo, one of the reasons they picked it, they had to find a place with a natural sinkhole. The hole where the dish is about 300 feet deep and 1,000 feet across. So that's what it looked like before we found it. And Dr. Bill Gordon's idea, obviously, to put it in Puerto Rico in Arecibo. There's 3 sites we wanted to find to put this telescope in Arecibo field, doing all those requisitions. So what we did, as you see, that's in 61. Minor excavation had to be done to put the dish where it is, and so we constructed the towers. Remember, again, it's 300 feet deep, about 1,000 feet wide, so we needed something in like a natural sinkhole. Remember, this is Karst Mountains limestone, so you can't make a hole that big. And I guess the biggest problem is where are you going to put all the dirt when you take it out? So we had to find something like a natural sinkhole. So once the towers were done, then we constructed the triangle. The triangle at the center of the dish. We raised it up a little, about 50 feet a day. Okay, once the triangle was up, then we put up the railings, the azimuth arm that spins. So then once we got all the azimuth arm and the railings up, we had to get a way to get up to the platform. That's when construction of the catwalk. So there's 2 ways to get up to the platform now. We've got a catwalk, and now there's a cable car. So there's the construction of the catwalk that's been finishing. So now you can see we can get up there. Now we have some of the drive systems up, and still kind of raw still. So once we got that, then we had to construct the dish. Okay, the dish. A lot of people think, you can see those pictures. The dish is not fixed to the ground. The dish is also actually suspended by a network of cables. So we put in the dish. The first mesh that was made back then, it was 1/2-inch chicken mesh. Okay, so that's what we did across the 1,000 feet, and that's the installation of that. So that's what it looked like when we were trying to put it in. Again, it's about 20 acres of this chicken mesh. And so finally, and the last pin came up, and the observatory was just about we were just ready to do science. And it got inaugurated in November 1st, 1963. A lot of the officials were there, the governor was there, and officials from the United States. So a lot of the science from then was basically atmospheric studies. It was named originally the Arecibo Ionospheric Observatory. So we saw that we had a lot more capabilities to do that, but we needed to upgrade. So the first upgrade project we did was to change the reflector. Okay, we needed to change the reflector to go higher in frequency. So we got rid of the chicken mesh. We gave it out to all the farmers in the neighborhood. What are you going to do with 20 acres of chicken mesh? So we just gave it out. It's still around anyway in the neighborhood. So then we put in 39,000 about these 3 by 6 foot panels. Okay, now this increased our reflectivity and accuracy. So as they're putting in the last panel. So with this, now we've got accuracy. Now we can do not only ionospheric studies. So now with the new surface, which now when we measured it, the RMS error across the 1,000 feet is less than 3 millimeters. Okay, so now we can do high frequency observations. One of the things that we do at the observatory, one of the things we do most is looking for hydrogen, neutral hydrogen in galaxies. Okay, so now we can do that, and that emits at 1420 megahertz. So now we can do that. Apart from that, we added a 2380 megahertz radar for planetary studies. Okay, then in '74, Joe Taylor, my good friend Joe, K1JT, you guys might know, right? And Russell Holtz, also a ham, don't remember his call, discovered 1913 plus 16 as a pulsar. And that pulsar eventually got him the Nobel Prize. Okay, so again, the research areas now we have research areas that we do. About 75% again is galactic studies, and 5% planetary studies, and we bounce signals off the comets, planets, and asteroids, and atmospheric science when we use the incoherent scatter radar. We have about 105 people working in the observatory. And 18 of the scientists, and they come from all over the world. And a good friend Jim also used to work there at the beginning there in the 70s. And we have investigators from all over the world, about 100 institutions. Many institutions are represented. So a lot of people ask, okay, so what have you guys discovered? And what's your contribution? A lot of things. So it's many things that we can't fit on this page. But a couple of things were people thought that Mercury rotated 88 days. When we found out it was only 59 days. Again, like I said, Joe Taylor won the Nobel Prize in 1993, proving Einstein's theory of relativity with that pulsar system. And we found out that Mercury had ice on its poles. So that's something that's almost inconceivable. But we did that. A lot of contributions in atmospheric studies, and also in the 80s and 90s, a lot of the maps for Venus were done. All the maps for Venus were done at the observatory. Venus is enshrouded with clouds. You can't see the surface unless you do radar. So we did that also. The first, also, and one of the big things, the first extrasolar planets were also discovered in Arecibo with Dr. Alex Foshan, which probably will win the next Nobel Prize. So those first extrasolar planets were discovered there. And a lot of the detailed maps of the strings of galaxies were also discovered. And one thing that, being a radial telescope, everyone asks, okay, so you guys look for little green men. Well, yes, in the background, we're always studying just in case. I mean, there's been a lot of search for extraterrestrial studies in the back. Now the government doesn't fund them anymore, they're privately funded. But we do, in the background, look for that one signal that might be coming from an extraterrestrial source. Again, yeah, so it's very difficult to find when you just to think that in our galaxy alone, there are like billions and billions of stars in our galaxy. And there are billions and billions of galaxies. So if you think there are more stars in the galaxy than there are grains of sand on Earth. I'm not talking about grains of sand on your favorite beach. I mean, imagine taking a bucket of sand and see how many grains of sand in that bucket. I'm talking about all the grains of sand on Earth. But it's huge. So, but again, with having said that, we haven't found anything. Okay, but you can do, if you do a search online, do SETI, right? Sugar Echo Tango India at SETI at home. You do a Google, you could download a screensaver which will actually use your CPU to download data from the observatory and put it on your computer and analyze that. This way you don't have to buy supercomputers, and use your computers to analyze this data. So yes, we do something like that, but in the background, again, nothing has been found. So with this, we also now we need it. So we got this. Now we need a second upgrade. Okay, the second upgrade, we had to put in a ground screen. The ground screen, what happens is that there's a long antenna, 430 megahertz antenna. When it comes off vertical, it starts heating up the sides, the mountains. And what happens with that? The system temperature goes up, and you can't find these weak signals. So we put in a ground screen. We put a new drive system that for the tie downs. Now we had added about 900 tons. Now when these antenna systems move from vertical 20 degrees, it'll tilt the platform. So we new drive systems, replace the line feed with a Gregorian reflector system. We had new receivers, now the S-band transmitter. We used to put out about 500 kilowatts. Now we can go up to megawatt, and the surface accuracy now is less than 2 millimeter. There's a picture of the extended ground screen. As you can see, that goes up about 80 feet, and that does keep the system temperature down. So the Gregorian system that we put there, we had to put this because we have line feeds. Again, this is not a parabola. The dish is not a parabola. It's a spherical dish. So all the signals do not come in to a point. They come in a line. What happens is these line feeds suffered from some type of myopia effect. So, you know, when metal heats and contracts, it expands. With the heat, it'll expand and contract. So to eliminate this, we put this Gregorian feed system in. The Gregorian feed system now, the signals would bounce off the primary dish. then a secondary dish was the top left, the top right one there, and bounces off a tertiary disk inside. That's what you see inside the dome. So after the tertiary, all the signals are focused into one point, and we have a rotating floor with feed horns, and we'll just change the feed horn into that focal point depending on the frequency you want to use. It's just a lifting of the dome. It's a big dome. It's about as Jim was saying, it's about a 5-story building. We'll compromise here. It's about a 5-story building. Some of the receivers, and you can see some of that red outline where it says Gregorian. That's the edge of the rotating floor. So those receivers are on that rotating floor I'm talking about. And this is inside the dome. Inside the dome, you'll see in the hole in the bottom left. That's the hole of the Gregorian. Then you see on the top left, that is the secondary. That's the secondary. I'll just come up here a second. The secondary is this, and this is the tertiary, is this part here. There's the third reflector, and everything reflects into the focal point right here. So this is the rotating floor. Okay. So yeah, so that you can see that again, you have the primary is the big one, the secondary, tertiary, and then the rotating floor, and that's the Gregorians, and that's the new Gregorian system, the feed we use, and that's the way. Now that's the way it looked in 1998, and that was one of the last upgrades we did. So with those upgrades, now we use for atmospheric sciences, we use that 430 megahertz antenna, which is that long needle-looking like antenna, and that's the one that when pointing down illuminates the whole dish. The transmitter on that is capable of 2.5 megawatts pulsed. Okay, 2.5 megawatts pulsed with about 60 dB gain. But then we have the planetary radar system where we bounce the signals off the planets and asteroids and comets. You'll see something like this. Okay, but now this one, it works real close to your microwave oven frequency. It works at 2380 megahertz. Now this is good for a contest. This one puts out 1 megawatt CW, okay, with 70 dB gain. Okay, so when we're transmitting 1 megawatt, we're transmitting 20 times 10 to the 12 watts, 20 terawatts. Okay, so when this is on, people don't want to be around that area. We're too close. Actually, somebody said, do you have any bird problems? You know, when we did the first test of this transmitter, inside the dome, everything focuses into that one focal point. Birds are real smart. They found out when they crossed that and the friends start getting zapped. Well, they didn't cross there anymore, but so birds learn real quick. They're much smarter than what we think. Okay, 2 minutes. Okay, and as you see, we found a rotating asteroid. There, we're going to go a little bit fast here. We only got 2 minutes. So, and then we got a new HF antenna system where we're going to be artificially heating the ionosphere and studying it with the incoherent scatter radar. And if it's going to be some dipoles that will be reflecting into that mesh you'll see hanging from the platform, and then off the big subreflector, and then we'll study the effects with the incoherent scatter radar. It uses, okay, that's more or less thing here. We're just a little bit faster here. It uses about 6 transmitters at 100 kilowatts. By the way, you guys want to know a little bit more about those antennas, you can talk to my friend Jim Braco, who designed them, WA3FET. They're sitting right here. Some of the, those are the transmitters. There's the mesh coming up. And you know, such a big dish, we need emergency repairs. If you know that is Pierce Brosnan during the filming of the movie GoldenEye. So there's Pierce, and we obviously have many users. There's Jody in there in the filming of the movie Contact. And I was actually lucky to meet both of them. And I actually gave them the tour, both of them. So it makes a lot of nice pictures. They took a lot of nice pictures, and it makes for a nice real QSL card. Okay, we also have many visitors from all over the world. And not only we do science, we also do special event stations. This was a special event station we did commemorating the 50th anniversary of the observatory. Everybody that contacted or operated the KP4AO got a little certificate looking something like this. And then we did something real interesting here. We did a moon bounce experiment. That's my brother from a different mother and father. That is Jim. WA3FET, my best friend. So I invited a couple of people to do this moon bounce. One of the guys was obviously Jim, my real good friend. We did JT65. We were going to do JT65, so who better to get than Joe Taylor, who wrote the program. So we did that, and we did this in April, and we made the cover of QST magazine in August 2010. So that's us here at the end. I'm not going to go through the contest station. We got a little contest station there. We've got not enough time. But also, the IRL also visits the observatory, okay? And every time we have the Puerto Rico State Convention at the observatory. So you don't have to, you guys can come down and get a tour, but don't have to wait. Don't have to wait for the state convention. You come down, I'll give you a tour personally, and I keep my word on that. There's a nice picture of the guys there with the ARRL visiting. And so a little tribute to my friend K9PG. And we'll see, doing a gentry there. You'll see Ward, Chip, myself, Terry, and Tim doing the gentry. So again, the observatory has given us, the scientific world, many new discoveries, many wonderful things in the world of science, but it's also taken and given a lot in ham radio as well. So not only science, we also do ham radio as well. As you can see, we did many special events and moon bounce. We'll do a couple of more things. And ladies and gentlemen, thank you very much. Thank you, Tim. Yeah, thank you.
You got earthquakes there?
Yes, we do. Yeah. We actually broke a cable on that earthquake. I had to go quick at the last time, but it's okay. Thank you, Terry. Hey, you got it there, you see? I guess it was my other arm was hiding that thing. Yes, sir.
Hey, I was at Green Bank about 2 years ago.
Oh, yeah.
Went up in the control room.
Yes.
Looked like somebody took a picture of the moon.
Ah, yes.
So that was where you all guys did an experiment.
Exactly, with bistatic. That's right.
Yeah,
we were transmitting and they were receiving. That's exactly correct. That's exactly correct.
So we still have 3 excellent presentations to go.
Get some
if
water.
you have missed antenniform presentations for the past 10 years, they are available.
Hey, thank you very much. Hey, how you doing? Hey, gracias too. Thank you very much. Hey, thank you. Thank you. All right, sure. Hey, thank you very much. Thanks. Hey, how are you? Thank you.
Dayton Hamvention antenniform.
Yes.
You can email me.
It's that thing weighs 900 tons.
Oh, so
it's
no issues with that.
no issues
Okay,
at all.
good talk.
Good. Thank you very much. Thank you. Appreciate it. Thank you. Hi. Hey, Van. So you're doing the gentry there.
Good talking.
Hey, thank you very much. Thanks, Dave. Thank you.
Screwed up, I guess.
So, yes. Started late. Hey, how you doing? Good to see you again.
Good. Thanks a lot. That was,
Hey,
that was
thanks. Good to
excellent.
see you. Thank you.
Really,
Thank you very much, Barry. Thank you very much. Appreciate it. Thank you. That's very much. Sorry to get. I almost looked at it.
It's okay. It's easy to forget.
That's a good thing. I didn't go to the bathroom.
It would have been totally my.
You're welcome. Wrap up this. Thanks a lot.
In the old days, which I almost go back to, before there were coax cables, nobody had antenna analyzers of the type we have today. What they did was they put RF ammeters in the open wire feeders or in the single line feed to an antenna, or it was an antenna. And basically, all you did was you tuned for max. You put the RF current into the antenna system, you thought it was going someplace. I think I've been pinned. Okay, let's see if we can get our wires straightened out here. There we are. And that was not a bad thing to do, because that's basically all you could do. Whatever you had up there, the more power you put into it, the better it worked. When we came into using coax cables, which was largely for hams after World War II, we then had a whole number of new sets of issues to deal with. We had to match the impedances everywhere, otherwise the coax cable would have excessive loss, and we'd end up with, instead of heating up the ionosphere, as they do from Arecibo, we would heat up the coax cables. And while that can be entertaining in its own way, it really didn't get us the kind of communications that we might hope for. So instead of worrying about RF current going up towards the antenna, we started worrying about power that was going towards the antenna and power that was being reflected back due to mismatches in the system in various places. Okay. Oh. Hit the wrong button. Uh-oh, now I'm in trouble. There we go. Okay, in case you're not familiar with them, these are some representative forward and reflected power meters. The one on the left is the very popular for many, many years. I started using them in 1960 something, I think, in the two-way radio business. The Bird model 43 forward reflected power meter. And you'd put the transmission cable from the transmitter in one end, put the cable going to the antenna in the other, and by turning the little slug in the middle, you could either read the power going towards the antenna or coming back from the antenna. And that worked very well, except nowadays each one of those slugs, you need one for each frequency range, and for each power range goes for, I don't know, a couple $100. So people started doing other things. Heathkit, of course, was quick to jump in at the time and provide a meter that did most of that for a lot less money, and also measured SWR. You'll notice that the power meter itself does not actually directly measure standing wave ratio. It measures the forward and reflected power, as we'll discuss in a moment. If we have the forward and reflected power, we can determine the standing wave ratio by that expression there, which is very easy to program on a programmable calculator or whatever. And many people, many watt meters came with little charts, so you just find the ratio of the powers and it would tell you what the standing wave ratio was. A nice thing about forward and reflected power meters is they not only tell us something about the antenna system, they tell us something about the radio, or they tell us the radio is putting out power. That's always a nice thing to know, because it doesn't always happen, as you all know. Some of them offer direct standing wave ratio measurement as well as power, forward and reflected power readings. Now, there's some downsides to the forward and reflected power meter arrangement. First is it doesn't really tell you what's happening. It tells you how well it's happening, how much reflected power there is, and in most systems you want to have minimal reflected power and at the same time you have maximum forward power. And that's a good thing to be able to do, but it doesn't really tell you what's causing the reflection. So you have to trial and error it. The other thing is, in order to get any data on this system, you've got to put out a fairly substantial amount of forward power. Now this means a couple things. You only can do it on the frequencies you're allowed to transmit on. Now in many cases, I don't know about you, the first time you put up an antenna, it doesn't look like it wants to talk to the radio at all on any ham band. So you've got to say, well, do I want to make it longer or shorter to get into where I can actually start making some reasonable readings? It doesn't really give you that kind of information. The other thing is, while you're adjusting your antenna, you're also interfering with anybody else that might happen to be using that frequency. Sometimes people are kind enough to listen first before they do this, but I have a sense that they don't always do that. Another thing, a little subtle point here, a power meter, reflected power, emphasizes high standing wave ratios when you're trying to take data. The reason for that is the 50% scale, if you have a forward and reflected power meter, and the reflected power is reading 50% when the forward power is reading 100%, that tells you the SWR is 9 to 1. Well, that's nice to know, but what you're usually interested in is much lower SWRs. So what that means is that the range of standing wave ratio you're interested in, 3 to 1, 2 to 1, 1.5 to 1, is compressed at the bottom edge of the scale. So it can be very hard. You know, it looks like you're getting rid of the reflected power, but until you can focus in on the very low edge of the meter scale, you can't really tell very well how well you're doing once you get close. So for example, in an SWR meter, the typical SWR meter that uses voltage readings, a 3 to 1 measurement is in the middle of the scale. Now you've got something you can much more easy to work with once you get down into that range. And so for 17% reflected power equals a 2 to 1 SWR. If that doesn't make any sense, don't worry too much about it. But it's just a little point. So what's in a power meter, or what's in a traditional power meter? Well, we have a indicator that measures forward and reflected power, and we have some kind of a display. In the simple ones that we used to have, the display is a meter, and we just have a coupled transmission line arrangement that separates forward and reflected power, and you can look at either one. It's fine, it works very well, but that's what it is. Now what about what makes it an antenna analyzer in today's terms? The first thing is we add a frequency generator, a generator of RF signals. Excuse me, that takes the place of the radio transmitter that we'd normally use. But the interesting thing that this picture doesn't show you is that transmitter is putting out 10 dBm signal or something, a very weak signal that can be transmitted via Part 15 rules and so forth on any frequency that you want, as long as you're not interfering too much with somebody else. So now we can actually measure the way our antennas work on all frequencies that the antenna analyzer covers. That's a big plus, because now you can completely I'm a CW man, what can I tell you? The analyzer can measure any antenna on any frequency that the analyzer covers, and that's a real powerful improvement in what we can do compared to the power meters. And let's face it, if you have an antenna that is giving you a low SWR on the band that you're working on, you don't really care too much anymore about what else is going on. You don't need an antenna analyzer. It's people who are building antennas or want to take detailed data about antennas or want to design an antenna tuner to match an antenna that can use an antenna analyzer. It's like most test equipment. If everything is working great, you don't need one. But if you put up an antenna and you don't know what it's going to do, this can tell you fairly quickly what's happening without you having to climb up and down and add and subtract wire. As you know, subtracting wire is much easier to do than adding wire. Now, that's a basic antenna tuner. These are the other things you can have in an antenna analyzer. What I've done is the blocks that are solid lines are the ones that were in the last one, and they're in all antenna analyzers in some form. The ones that are in dashed lines and the connectors and connection interfaces are things that can be in antenna analyzers. And this is what makes the difference between one antenna analyzer and another. The very basic antenna analyzers have an old type VFO like you'd have on a 1940s receiver, and you can read the frequency to 0.5 megahertz, and as you go higher in frequency, the readout gets less and less and so forth. Those are usable, but you really need to be able to tell what the frequency is to know what the antenna is doing. So if you want to use one of those, you almost have to have a receiver next to it or a frequency counter that allows you to determine what the frequency is. Then you can tell the frequency. But some of them have either a frequency counter built in, which is very handy, so you don't need another piece of equipment, or the frequency generator itself is a DDS oscillator, that direct digital synthesizer that generates an accurate frequency. So you can say down to the hertz or the kilohertz or whatever, depending on the model, I know exactly what frequency my data is being taken at. So that's very important. The other thing about that is some analyzers allow you to use the frequency counter as a separate standalone frequency counter. And when you bought an antenna analyzer, you also get a frequency counter. It may not have the resolution or the accuracy of a $12,000 HP counter, but it has a lot more accuracy than no counter. And so a lot of people find that very useful. I've shown another interface here that many antenna analyzers have a computer interface. We'll show some of the displays that you can get. And that can be very useful both to define the tests, to sequence the tests, depending on the particular analyzer, or to collect data. There's nothing better than having, instead of scribbling things on the side of a pad and trying to figure out what they meant the next day, nothing better than having an actual screenshot that says, this is what my antenna measured before the snowstorm, and this is what it measures now, and now I can see what the changes are. Makes it a very useful kind of thing. Another thing that's very handy is some antenna analyzers have built-in power supplies or rechargeable batteries, that kind of thing. And all of these dotted lines may or may not be in any particular antenna analyzer, depending on what features they have. So what an antenna analyzer has that separates it from other kinds of power meters is built-in low-level signal source that you can use on any frequency. An indication not only of forward and reflected power or standing wave ratio, but actual antenna impedance. I shouldn't say antenna impedance, actual system impedance of whatever you're connecting to the analyzer. Some just indicate the magnitude of impedance, and frankly, I've never quite figured out what to do with that. But most give you also the real and imaginary part, or the resistive and reactive part of the impedance. And some of them give you the sign of the reactance, which is particularly handy. By the way, if you don't have the sign of the reactive part, so you can't tell if it's inductive or capacitance, if you move this frequency slightly upward and the reactance increases, it's inductive. If you move it slightly upward and the reactance decreases, it's capacitive. There's a caveat there. You have to be very careful it doesn't dip down through zero in between. But as long as you move very slowly, because then you're on the other side of it. But so you can tell that yourself if you're very careful and if you have a very slow tuning rate on your antenna analyzer. One of these with a dial type tuning, forget about it, I think, in most cases. Some of them provide swept frequency analysis, so you can not only see a particular frequency, but you can see a range of frequencies all in one shot. We talked about the frequency counter and the use of computer memory and display. So those are all the kinds of things that you can get. Now this next display is a SWR display, and it sort of shows you the kind of information you can get on this particular one is a Rig Expert AA54. It happens to be the one I use. But there are a lot of other ones that give similar data and similar kind of display. So this is telling you to 3 significant digits what the SWR is, which is handy. It's giving you the frequency that you're measuring it on. It also gives you a bar graph. And that is particularly useful. I don't know if any of you have tried to adjust something while looking at a digital display, and you turn the dial and you get a different number. You say, well, let's see, am I going the right way or am I going the wrong way? If you have a bar graph or some other kind of a virtual meter you can actually get a much better feel for how to adjust your antenna or whatever. You can use these to adjust the antenna tuners. And that is much better than just a single reading that you get on a meter dial, in my opinion. Now let's talk about what we're really measuring here. This is a series impedance model of an antenna. What it is you have a resistive part. As we mentioned, we have a reactive part. And the reactive part will be combined when you read it. It'll be the combination of the inductive reactance and the capacitive reactance, so that you have one or the other, depending on whichever one is larger, you'll have the net difference. Okay, so it's a R plus JX is the way we refer to it, and it's a plus sign if it's inductive and it's negative if it's capacitive. Now, so you can get that kind of information from your antenna analyzer. Here's another screen from the same antenna analyzer. You put in the frequency, gives you the SWR, and it gives you that series model. It gives you the magnitude of the impedance, the actual resistive part, the reactive part, and the negative sign indicates it's capacitive reactance. And it tells you, just in case you're interested, that actually is equal to 637 picofarads. Kind of everything you'd want to know about what you're measuring at that antenna port. Okay? Almost everything, because of course you're measuring that. One of the problems is you're measuring that at the bottom of the coax cable, not at the top where you're really interested. And I don't know if I can go back. Can I go back easily? Not easily. Okay, so we won't do that. What we'll say is the antenna analyzer can't tell whether you're whether what you're measuring is an antenna or a couple of components, a resistor and a capacitor. It can't tell the difference. It looks the same. Now that may be good news, because if what you really want to do is not measure an antenna, but measure a capacitor, you can measure it with this. And it's a great handy tool to measure components. You got a box full of components, you don't know what they are. It's got this little capacitor with strange colors on it and two leads. You clip it on your antenna analyzer and you get a frequency where it looks reasonable, and you'll measure the capacitance. And if you measure the resistance, that can tell you the Q of the capacitor at that frequency. So a very handy kind of thing to have. And it basically replaces an impedance analyzer, laboratory impedance analyzer, for a lot less money. Another thing that antenna analyzers can do, some of them can do, and more are doing this, is they can provide multiple frequency data at one time. So you hook it up. Here I've asked, this is my coupled resonator 6-meter Yagi, and I've put in the center frequency of 50.2 megahertz and said I want to see what the SWR is from 50 to 50.4. Hit the button, and here's the plot I get. That's kind of handy, isn't it? So I don't have to go and take multiple points of data, and I can not only see what the SWR is at 50.2, but I can see if that's the lowest SWR or if that's, I need to move it around in some way. So that's a very handy feature of many antenna analyzers. Another kind of multiple frequency data here, you can actually, instead of getting the SWR, you can get the real and imaginary parts of the impedance plotted over the frequency range. This is a different antenna on different frequency range, but the same idea. And then a really slick thing of the Rig Expert one that I have, oh damn, sorry, pardon my language. I double clutched there or something. Anyway, it gave you the SWR of 5 frequencies simultaneously. Why would you want that? If you ever had an antenna that has interactive tuning, multi-band antenna with interactive tuning, and you get it just right on one band and the other band is fouled up, you go back and you adjust that one and the first band is fouled up. This shows you all up to 5 frequency ranges at the same time. Very slick idea. This particular chart looks very busy, and it is very busy. This is, I don't know if you can read all that stuff. I can hardly read it here. But this is a offline program that comes with the Rig Expert that provides a whole bunch of data over a frequency range that the computer can capture. So you don't want to take this up on the tower with you probably, but you can do this on your bench. It gives you a whole set of data across the whole range. You can slide your cursor, and I have a dashed line where the cursor is on the computer, and it's giving me the frequency, the SWR, the return loss, the impedance, the magnitude of the impedance, phase angle, and a whole bunch of other things. And by the way, you don't have to print all those. You can just have 1 or 2 or 3 if you want them, but I just put them there to show the kind of thing that you can do. So this gives you the kind of information. I guess what I've tried to summarize here is the kind of information that you can get from an antenna analyzer. And again, each different model has different features and different details of what they give you, and it's important to look and see what they have and what you're interested in. But this is kind of a representative one of fairly sort of a mid-range antenna analyzer. Now what happened? Okay. All right. Let's take an example here. We have an antenna, horizontal dipole, up in the air someplace. We have a coax cable, and we have the bottom end of the coax cable that we can reach. Now what we usually want to know is what's happening at the antenna. We can't usually measure that. And even if we could, even if we get up there and put the antenna analyzer right at the antenna, we have the kind of problem that if you stand next to the antenna with your hand on the antenna analyzer, the number you get is not the number that would be there if your hand and you weren't there. So you don't want to do that. Most times, there's some exceptions to that. So you have to measure it at the bottom, and that tells you what the antenna system impedance is, but doesn't tell you what the antenna is. And it can be very confusing sometimes to try to interpret those results, because you may get a completely different answer to what's happening. In other words, at the bottom, you may think, oh, this is low in frequency, I've got to make it shorter. Well, it turns out because of the transformation in the mismatched coax, it actually may be the opposite way around. So it's important to know what's actually happening at the antenna. So what do we do about that? Well, one thing is the number that you get there is exactly the number that you want, the number at the bottom of the coax. If you're not going to change the antenna, but you want to use an antenna tuner to match that antenna, because that's the impedance the antenna tuner will have to deal with. But if you want to know what's happening at the antenna, you can either use a Smith chart or a software like TLW that comes with the ARL antenna book, and make a translation to determine what the impedance is up at the antenna. And that's very important that you do that before you do anything dramatic with the wire cutters, unless you've got a lot of extra wire. Okay. So let's take an example of that real quickly. We'll take our horizontal dipole antenna, and this is a measurement at the bottom of 100 feet of RG8X from a 20-meter dipole, and it gives us all the impedance data that we've had before. And so what we have, the key data is we have an R of 52.8 and an X of minus 17.7. Now if we go to Dean Straw's TLW software and we click on the box that says input, this is what we measure at the input to the transmission line. Notice I've got the 52.8 and minus 17.7. Up at the top I've selected RG8X transmission line, 100 feet, frequency 14.112. And immediately down here at the bottom, I find out what the SWR is that I'm measuring at the bottom, 1.39, which is about what I saw with the antenna analyzer. But what's really the SWR at the other end, at the antenna, and it's always higher than at the bottom, it's 1.56, not too terrible. But the important thing is that we look here, and the impedance at the antenna is actually 34.65 plus J9.82. So just as I discussed before, we're reading an antenna. If we made our decisions at the bottom of the transmission line where we see capacitance, we'd think we needed to make the antenna longer. But the antenna is actually inductive, so we need to make it shorter.
3 minutes.
Okay, 3 minutes.
The only question I have about this, in case of the feed line, is noted that, of course, the characteristic of the feed line is what we calculated, in addition to the loss of the feed line.
Yeah, it's all taken into account here. Let me suggest, since we have 3 minutes left, I've got posted Doctor is in times 3 one-hour sessions over there. Maybe we can take your question separately. I'm sure it'd be of interest to other people, but unfortunately, I don't think we'll get through the thing if I don't go. Or if we have time at the end, we can take it. Okay? Sorry to do that to you. Okay. So what do you need to really tell what's happening is you need to be able to to model and simulate your antenna to find out what impedance you'd expect. And you can do that with EasyNet or some other NEC-based software. And then you need some kind of transmission line analysis program to make the transition. If you're starting at the bottom with measurement data and want to find out what's happening at the antenna, that's what you need. Or if you model the antenna and say, what should I expect at the bottom of my transmission line so I can see whether the antenna analyzer is indicating I have what should be there, that kind of program can help you. So I guess my point is it's important not to just take measurements and run around with wire cutters. It's important to understand what you expect, understand what should be there and what you want to get from it, and then make the appropriate translation. What else can you do with an antenna analyzer? Well, an antenna analyzer might be the most useful single piece of test equipment, but maybe you need a VOM first in your shack. But all of these things, it acts as a signal generator. It doesn't have an attenuator, it doesn't have a calibrated level, but with a addition of an attenuator, you can get that. It can work as an impedance bridge, as we've discussed. Some of them can work as, mostly the MFJ ones in the mid to upper price range, also can serve as a frequency counter. You can make it act like a grid dip oscillator or gate dip oscillator, depending on when you grew up. You can measure the electrical length of transmission lines, and you can actually determine the loss of a transmission line, whether it's open or shorted. So
distance to loss, to failure sometimes.
Yes, there are some of the rig expert ones actually have a time domain reflectometer. So if you have a short in the line someplace, you can actually see where it is. That's very handy. That's the only one I know that does that. They do. Oh, do they have one now too?
Yeah,
they keep adding a new one every month.
259, I think he has it in the menu.
Ah, okay. Wasn't aware of that. And there's a lot you can say about antenna islanders. I could write a book about it. In fact, I have. And called Understanding Your Antenna Analyzer.
And everybody gets a free copy.
Everybody gets a free copy if you just pay, I think, $29 at the ARL desk there. So, short word from our sponsor. We have other books we've written. And with that, I will say thank you very much for your attention. And if you think of questions, by all means, the doctor's always in. Send an email to W1ZR or doctor@arl.org, and I'll be happy to answer your questions about this or any other technical subject. Thank you. Pull this out and take it home.
Thank you. Thank you very much, Joel. I want to get Tammy up here. How many folks in here watch Ham Nation every week? How many go to the spaceweather.tv website? How many live for the Space Weather Update with Dr. T? There we go. A few fans here. We're very proud and excited to have Dr. Tamitha Skov with us here at Hamvention. She is not currently licensed, but Gordon has supplied the study material. We're sure she's smart enough to do it. So I think this summer you'll see a new ham. And we also want to thank the Yasmin Foundation. They provided a grant that brought her here today. And if you want to go ahead and get your slides and movies ready.
Get them up. Is this thing on mute? Is the mic on mute?
No, that mic is on the internet.
Oh, that's just on the internet. Okay, so I use this one?
Right.
Okay.
So please give a very warm welcome to Dr. Tamitha Skov.
If I can find it, is this it? Okay. Hi there, thank you so much. I appreciate you guys being so warm to me early on here. I will ask first of all, does anyone have a laser pointer I may borrow?
I do.
Fantastic, thank you so much. Because otherwise this will be, I'll have to use this little...
It's the middle.
It's the middle one? Haha, the middle. The middle button, that's the only button there isn't one.
Yeah,
it's up on the top middle, okay. Okay, so can people see this? Okay, great. Okay, hopefully this will go without a glitch. This will be a little bit different of a talk than what you're probably accustomed to. Unless you've seen the Hamnation videos, you know that I do these weather forecasts. So I'm going to give you a little bit of insight into the science of space weather and how we predict it. And the funny thing is, when I was putting this together, I was a little bit nervous that this might not be the right audience. And then I sat on a plane next to a father and a son. I believe his name was Rob, and Sam was the son, who I think is talking in the youth forum tomorrow. And he told me this story about how he had to convince the school that his son was going to let him out for a day, because by going to Hamvention, he was doing science. And as he continued to tell me this story, he said that he went from this teacher who was looking at him, kind of stabbing her foot and crossing her arms and kind of like, yeah, you want to get your boy out for what? She went from that posture to, oh my gosh, can we give your son extra credit for this? And when he told me that, that's when I knew that I'm going to be reaching the right audience. So. And of course, as Tim mentioned before, big thanks to him and also the Yasmy Foundation. Of course, Hamnation as well, especially Don Wilbanks and Bob Heil and just everybody, Gordon, all of them. Land Lamphere, he's helped me immensely with Space Weather TV. We're still trying to get it up and running. You'll see it up, down, that type of thing, because it's all kind of run on a shoestring budget here. And Radio Waves as well. They've really helped me get the word out to you guys. Much appreciated. Okay, so what is space weather? Well, essentially, space weather is a planet's interaction with its host star and the surrounding space environment. But that's pretty general. That's very general, but in more serious terms, it actually occurs at planets and at moons, at comets, asteroids, and other celestial bodies in the universe. If we kind of rein it in a little bit and look at just our solar system, we actually see aurora at Jupiter and Saturn, and we see at Uranus and Mars. Effects are studied at the moons Io and Europa and Ganymede. Those are Jupiter's moons, and Saturn's moon Titan. But we're going to highlight sun-driven processes. We're going to rein it in even more, just stuff that is affecting the Earth. And what we won't cover are things like galactic cosmic rays, anomalous cosmic rays, micrometeoroids, interstellar dust, space junk, man-made or not. None of that stuff. That's all still space weather and fantastic stuff to talk about, including like near-Earth asteroids, as we saw with the Arecibo radio telescope, but not really the focus of this particular talk. So let's get into it. What our star, it's basically a giant fusion reactor that drives all of space weather. And because it's a big fusion reactor, we have energy output that comes in all kinds of forms. We have electromagnetic radiation, which you guys are very familiar with. This is from X-rays all the way down through radio waves. We have solar wind, plasma, and magnetic fields. And a lot of the most active of the magnetic fields come from sunspots. And these things are oftentimes much larger than Earth themselves. We also have solar flares, and all of these are distinct phenomena, by the way. Solar energetic particles, which we also call solar radiation storms. You'll see them referred to as SEPs. And then coronal mass ejections. These are CMEs, and these are not the same thing as flares, and they're not the same thing as solar energetic particles, but they oftentimes happen at the same time. That's why it's so easily confused. So what do space telescopes see? I mean, because of all of this stuff, we have to stare at the sun in all different wavelengths, basically all different frequencies. It's kind of like looking at it from different frequencies of the ham bands. Every time we look at a different frequency, we're actually looking at a different temperature on the sun, and that translates to layers on the sun. For example, down at about 5700 C, you're looking at the white light. You see sunspots there? That's basically the surface of the sun. Kind of what everybody sees when they look in the sky. A little bit higher in temperature, you get a little bit further out from the sun, and you start seeing some of the electrical connections and activity that are connecting these sunspots. When you go even higher, oh, by the way, this set of pictures, all the same moment in time. When you go higher in temperature, now you're beginning to get out into what we call the transition region. This is the chromosphere. This is where we start seeing a lot of activity, because the solar atmosphere is very, very turbulent, and there's a lot of things going all the time. Going even higher in temperature, and we get, you start seeing the atmosphere. Even higher, you start seeing magnetic field structures. Like here you can see in this one, you can actually see an ejection coming out, and I'll focus on that in a minute. Here you can kind of make it out, but not really. And then here at some of the hottest temperatures that we measure at 131 angstroms, and I'll show you this in a little bit more detail. You start seeing that structure again, but now you also pick up flare activity, and it's very, very bright. So if you want to know more about these temperatures, I'd love to go into them in more detail. I can talk with you after, or you can actually go to the SDO website and they'll explain to you what all this stuff is. But that's why if you've ever seen false color images of the sun, why are all these different colors there? It's because we're actually looking at different regions. So that's not the only way we image space weather. We also look at coronagraphs. Now coronagraphs view much further out in space. They can see beyond the corona. As you can see here, that little white thing right there, that's the sun. The blue thing is an occulting disk that blocks out basically all of the corona of the sun, so you don't notice, so it doesn't black out all of the stuff that's going on here. See that beautiful thing right there? That's a solar radiation storm. You think it only affects Earth, but it doesn't. It affects our space telescopes too. If I click, this isn't showing my screen. So how do I click on this other movie? Because this movie down here also, this one also moves. Can it share that?
It moved a little bit.
It started? See, we didn't check it on the screen. We checked it here, but not once they turned the screen. Well, that's going to be, well, okay. So I probably won't be able to play this one, but what this is even further out. So this one goes out to about 30 solar radii, which is about 15 sun lengths from here to about the edge of the screen. And you saw that there were little transient stuff. It's not just a quiet solar wind that's blowing out. It's kind of the sun's atmosphere just blowing out. And if you go even further out, here, you're not seeing it, but this is actually stuff that's blowing out from the sun, and this image is all the way to the Earth. The Earth is on the other side. How did you do that? Beauty. Thank you. This is called the heliospheric imager, or HI. And so you're seeing all of this wispy stuff. These are coronal mass ejections. These are solar storms that are being blown off into the space, and they eventually propagate all the way out to Earth. So I'll let that run for just a second. Okay, so these are the ways that we look at the sun and look at how these structures are coming at us.
What's the distance between left and right side of the screen?
1 astronomical unit, about 1.5 times 10 to the 8th meters or kilometers. I can't translate that to miles. Sorry about that. Okay. Now, oh good, I've got this. Okay, so I can do this. Okay, so we have the quiescent sun. That's basically solar wind, very quiet. In this quiescent sun, we do have high-speed streams, so we have sometimes very fast solar wind that comes out, and it can slam into slow solar wind in front of it and cause slight problems. And it can also sometimes, if it's strong enough, can cause actually interplanetary shock waves. But really what I came here to talk about is the active sun. And here we have solar flares. That's one of the first big things. Let's see. Boy, that was weird. Okay, so you'll see a solar flare along with a coronal mass ejection, boom, right there, and then you see this nice jet of plasma that comes out. Now that's one type of thing. Now the solar flares, they can cause energetic particle storms, which are mainly protons and electrons. These are very energetic particles. If you're familiar with the lingo, it's like 1 MeV and above. And of course, because they're so energetic, they have near speed of light travel. It takes about 8 minutes for light to reach Earth. These arrive from 8 minutes to maybe an hour or 2, but they're there very quickly. That's why when you have a solar flare on the sun and very shortly thereafter the ham bands go kaput, that takes about the time for light to travel from here to the Earth. Now, here's the difference. CMEs. When people say, well, aren't flares and CMEs the same thing? No, 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 not at all. They get very confused in the news, and you'll see, I'll show you an example later, but let me play this. Now, coronal mass ejections oftentimes happen at the same time as flares. Here's a perfect example. This is that one I showed you earlier. It's much more massive and much more slow, and it's got a loop shape because of the magnetic field. These are electrified charged particles that are forced to be constrained and to move around the magnetic field. So the magnetic field of the sun dominates how these things move and where they're allowed to go. And you can see as we propagate it out, there's the sun there. This is the same image, this is SDO, and now we're out in coronagraphs. You can still see that loop structure clear out to 30 solar radii. And Earth is a tiny dot. This structure is much larger than the sun. So you can imagine, by the time it reaches Earth, by the time these structures reach Earth, they are about a quarter of the distance between the sun and the Earth. That's how big these things are. Okay, these structures are the ones that cause geomagnetic storms. Okay, so speaking of, let's talk about the Sun-Earth system. The near-Earth space environment is vast and complex, and the solar phenomena, they're just a first link in a very complex chain of events that lead to effects at the Earth. Now, I'm not going to go through all of this here, but it's just giving you an idea that you have the sun, you have coronal mass ejection, you have a shock wave that's driven in front of this, you can have solar particle events which cause disturbances in the ionosphere, it energizes radiation belts. This thing here is the Earth's magnetic shield, we'll call it the magnetosphere. You can have solar or magnetic storms, these geomagnetic storms. They can cause upsets for spacecraft charging and all sorts of issues that I won't go into, it's way too much. And I'm not even getting into all of the microenvironments that occur inside the Earth's shield. I'm skipping that entirely. But what I will do is give you an overview. Now, hopefully I can mute this. Is there a way to mute this? Because I don't want you guys to hear the audio of this. It's got music. We don't need to hear this.
It's already muted.
Oh, is it muted? Because hopefully at one point I'll be able to unmute. Because because I actually have some sounds that I'd like to be able to play for you guys later on. But what I'm going to do here is kind of give you an overview if this movie will play. Oh, come on. It's playing on my screen. It's not playing there. How does that work?
Obviously not good.
Has that happened before?
No.
Don't you love Microsoft?
There's no way that I don't know how to deal with it.
Oh, come on. Really?
I don't know how to deal with it.
Holy poop. Okay.
I can't even stop it.
Well, we should be able to stop. Can we stop it? There. There. Oh, it's doing, is this doing like a second screen? Is that what this is?
Yeah.
Oh, well then I just do that.
Yeah.
Why don't I do it that way? So we put it on a secondary screen for some reason. Yeah, how many physicists does it take to figure out how to run Microsoft? That joke was unintentional. I really meant it. Okay, let's try this again here. Start from the beginning. Okay, good. So this is the sun. This is the white light version of the sun, and we call that layer the photosphere layer. So here's the sunspot I was talking about before, and again, these things are much larger than Earth typically, and that's where all the active stuff happens. But when you get into the chromospheric layer, a little bit higher, you don't see those sunspots nearly as clearly. But if you notice, that's where all this activity happens. Here's a gorgeous view of a prominence eruption. This is a coronal mass ejection. See it twisting and writhing? That's the magnetic field that's forcing it to wind itself up in a braid. So as we pull further out in space, now you're starting to see these eruptions that come out, really the solar atmosphere coming out way past just the corona like you see with eclipses. But there's something going on all the time. Here is a flare in 131 angstroms. That's a lot of X-ray, radio bursts, X-ray noise, all sorts of stuff. Here it is in the same flare in 171 angstroms, slightly lower in energy. Now watch, you'll see the blast waves. See those blast waves? This is when in the time in the videos I go boom, and it goes boom. This is a coronal mass ejection. Look at this. This is much slower stuff, but look how much material comes off. These are the slow lumbering things. This is it, that same event in a coronagraph. And as it lumbers towards Earth at a much slower pace, it gets there in about 3 to 5 days. These are the ones that really rattle the Earth shield, and I'll show you in just a second. So as we back away from the sun and we see the artist's rendition of this is that solar storm coming out, if it first encounters a planet like Venus that has no magnetic shield, what happens? Well, these particles and field and everything just rip right through the atmosphere, rip off electrons, just literally try to tear the atmosphere off of that planet. But at Earth, when it reaches Earth, it's a totally different story. See how the particles are getting deflected around the planet a bit? The very same magnetic field you measure with the compass here on Earth extends up into space, and it's our magnetosphere. This is what I call the Earth's magnetic shield. And it's very much like a bar magnet, like a fridge magnet. You got a north pole and a south pole, like a dipole, and it wiggles all the time. So it's always moving, and this causes currents down here on Earth. Now, let's take that dipole field and let's put it in a solar wind where you're blowing from the left against it. Well, you end up crushing the front end and you end up pulling out the tail in the back, and kind of like a comet tail. We call that the magnetotail. Now, when a solar storm hits, something very interesting happens. If it's got the right magnetic configuration, it's like the magnets that click, and it's able to strip out part of the field away. It's able to shoot particles up in from the magnetotail, just like a slingshot, and it shoots them right down the poles. And this energy, these precipitating electrons, well, it's just electricity. It heats up all the radiation belts, and it causes aurora. And this is what you see. So the aurora really is the Earth's shield's way of exhausting all of that energy that it gets from these solar storms. Kind of neat, huh? Just like a neon beer sign. But this is why we have SDO. This is SDO. This is our big sun gun with the big 4 cannons you just saw. That's the one that stares at the sun and gives us all those pretty color pictures so that we can monitor whatever the sun throws at us 24/7. Okay, now let me move this out of the way or kill it. Good. Okay. So I'm skipping over all the magnetospheric stuff because it's really not as relevant to the ham radio world as is, of course, the ionosphere. I'm not going to preach to the choir here because I know you guys all know about this stuff, but the ionosphere is a charged plasma layer above the atmosphere comprised of ions and electrons. And it would be neutral, but it gets charged exposure mainly to the sun's UV radiation. So that's why if anybody ever wonders why is propagation different on the sunlit side compared to the night side? Well, because you have photo emission, and you're able to actually cause neutral atoms and particles to ionize. And as soon as you have ionizing particles, then this thing becomes electrically charged, and radio waves have to suddenly see it. It's no longer transparent to radio waves. So this charged nature facilitates radio propagation. Now, during geomagnetic storms, those caused by that big CME I was showing you, extra energy caught in the Earth's magnetic shield gets dumped into the ionosphere. And this energy basically is a flow of charged particles, mostly electrons, but some protons as well, lights up the plasma in the Earth's ionosphere similar to a fluorescent lamp or neon sign. And the result is the aurora, as you see here. You got the northern lights and the southern lights. And if I can click on this movie, which I will now move over, the reason why I'm showing a little bit of aurora is because you can start seeing some of the dynamics of the aurora. Every single one of these green arcs, you can see the field. The reason why they've got these vertical curtains is because this is the direction the electrons are precipitating in. And you can see it's very dynamic, and there are threads and currents and all these, it's not homogeneous. This is very layered and structured. Do you see these bands? All of these represent individual current tubes. And so trying to understand how this stuff changes in the ionosphere, especially how it relates to propagation, is extremely difficult. You can imagine it's a very challenging science. That's really what I wanted to show here. Okay, so next. So talking a little bit about, keeping that in mind, what that aurora kind of gives you an idea of what's going on in the ionosphere and how incredibly striated and how incredibly tiny the scale sizes are of these space weather effects. Most of you will recognize that I'm kind of talking about the ionosphere here. You've got the D region, E region, and F region. This is obviously an artistic diagram, but it's probably a little different than what you're used to. From the point of view of, you're not seeing smooth surfaces here. I purposely made these layers very warbly and to kind of give you a better idea of what's really happening. If you think almost like the surface of an ocean, the ripples in the water, they're constantly changing, they're never the same, sometimes big, sometimes little. There are things like winds and waves and currents that are constantly moving. And this is the surface off of which your radio waves must propagate. It must bounce, reflect, and also all sorts of things can happen, as you can imagine. We have things like atmospheric heating instabilities. People call this plasma bubbles. You literally have hotter air, neutral air coming up and welling up, and it pushes up against the ionospheric layers, pushes those layers up and creates a plasma bubble, and suddenly now you've got a bunch of neutral particles where there used to be charged particles, so your propagation goes away. Well, what happened? How long is it going to last? How big is it going to get? Depends upon the thermal aspects of the atmosphere. You have things like currents in charged particle regions. That changes conductivity, so you can have layers where sometimes the ionosphere is really conductive and sometimes it's not, and it could just bounce back and forth very, very quickly. You can also have things like signal scintillation. Anybody see, you've ever been to look at the night sky and you ever see the stars twinkle? Like twinkle, twinkle, little star, and you wonder, that visual, you see how the light comes in and comes out and fades in and fades out? That is exactly, when you guys get signal fades, that's exactly what you're hearing. You're hearing twinkle, twinkle, little star. It's exactly the same thing. So I bet you'll never, now that you know that, I bet you'll never sing that song the same way again. But anyway, you get reflections, you can get refraction where the signal bends. This is actually even worse for GPS because suddenly the satellite, thinking that this is a straight line down over here, suddenly thinks it's somewhere over here. That's a real problem for them. For you guys, it may actually enhance propagation at times. Depending upon the conductivity, you can get ducted waves that then will bounce, 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 bounce all the way around the world. But these things are very transient. And right now, the state of space weather for the scientists is that we actually look at longer term trends. This weather is really tough, and we don't have enough satellites right now and measurements to be able to catch these small scale, short-lived phenomena. Yes? Whoops.
Isn't the F layer actually divided into two layers in the daylight hours?
In the daylight hours, yeah.
And at night, of course, it combines back together.
Right, right. And this is so simplified. Yes, so thank you for keeping me honest. But I just tried to make this, because what I'm focusing on more really are the things that you won't see in a typical ionospheric book about radio propagation. But yes. You also have sporadic E. I didn't put that in there either. So. Okay, so this is where I'm hoping I can turn the sound up. Is it possible? I mean, I can do this here. Come on. Now, we'll see. We'll see. So we decided to give you some ideas of what space weather interference sounds like. This was an X2 solar flare. This is a R3 level radio blackout. And I'll get to what that means in a minute. You can actually see it in this plot here. Whoops. You can see it in this plot here. Here's the propagation from like 3 to 30. And then you've got the people talking. You've got your signals here. And then suddenly a solar flare hits, boom. And basically everything just goes away. So you'll hear that here, hopefully. So the bands are already getting bad. Can you hear people talking? No. Didn't hear people. Did it start at the beginning or not?
No.
Oh, thank you. I don't like this new version of Windows. Okay, let's try it here. Okay, did I mention it?
Have a good day, 73 KFMRE. Yeah, what happened is bad. Is I losing now too? We got a solar flare or something.
Very savvy operator. And then pretty soon after that, it all dies. So I'll stop it. Whoops. Go back. Okay, so that's one type of thing. Some of you may have been lucky enough to hear dawn chorus. Let's see if I can. Have anyone ever heard this? These chirps are actually due to particles from the Earth's radiation belts. There are all sorts of waves and instabilities that happen in the radiation belts that try to get rid of this excess energy. And sometimes when these particles are knocked out of certain areas, it creates waves, radio waves, that will then propagate down into your antennas, and you'll hear these chirps. Now, there's also spherics and twerks, or tweaks rather. Twerks, hello. I'm at the wrong convention for that. So here's some spherics. Now they're basically the same thing. They're from lightning nearby, but spherics are really close, and then tweaks are a little bit further away. Boy, am I fighting this guy. Sounds like bacon frying. Recognize that? Lightning. Lightning real close. Okay? Now, let's see if I can stop that. Next one. This is tweaks. Now tweaks are essentially lightning that's a little bit further away. So what happens is that you're able to hear a dispersion. This is the higher frequencies reach you faster than the slower frequencies. It's like running a race and the higher frequencies are faster. So it spins it out a little bit. And so you get this kind of noise. Boy, that's loud. Sorry. Does that stop? Okay, good. Okay, and now the last one is whistler waves. Now this is lightning that's even further away. This lightning can be hundreds, if not thousands, of miles away. The sound actually from the lightning strike propagates all the way up into the magnetosphere, into the big lines, big magnetic field lines that stretch way out in the dipole field, and then propagate all the way around the world and back again. And you can actually see these. Well, you can actually see these here. These are whistler waves. So what you're going to hear is a nice long tone. Yeah, loud. Sorry. I didn't expect it to be that loud. Anyway, so those are some classic space weather sounds that you will actually hear when you're on the ham bands, and hopefully now you'll be able to identify them. So how bad can space weather be? Well, I'm not going to go over this, but NOAA actually has some space weather scales. They have scales for geomagnetic storms, which are caused by the coronal mass ejections, the big massive storms that come at us. That's the G scale from 1 to 5, and they've got a pretty good description here. So I would urge you to go to SWPC, that's at NOAA.gov, to read up on these if you haven't already. Solar radiation storms, these are mainly particle events. These are the solar radiation events. That's the S scale. And then solar flares, that's for radio blackouts, and they've got a scale from R from 1 to 5. So R 1 to 5, S 1 to 5, and G 1 to 5. Okay, so what I'm going to talk about is what is a typical solar storm, what is it like, and give you an idea of the kinds of effects that we see. Well, this is a period from, I think, this is about a week long, from the end of January to the 1st of February. And what we had down here, you don't have to read any of this stuff, but you can see the peak here. This was actually a big M-class flare. This was an X-class flare that happened a couple of days later. This stuff often happens in series. And so when you get one, you get more, you get another, because you'll get one bad actor on the sun that just wants to keep playing it off over and over again. Oftentimes when you get these flares, you also get particle radiation storms. So here's 2 that happened with those 2 flares. And of course, you'll get a CME as well. 3 different phenomena happening nearly simultaneously. Okay? Now, from this, we had an R2 and an R3 radio blackout, which made the ham bands go completely away. We had S3 radiation storm, a G1 to G2 minor geomagnetic storm, and all of this lasted over an entire week. So how does this affect the HF bands? Well, not just mentioning that ham radio was terrible, but how about this? Now, I'm sure some of you know DRAP. Color means bad on this map. This is a solar flare. This up here at the high poles, these are due to the particle radiation storms. And back on, I think it was the 27th of January, the FAA Radio Communications Center reported that the Central East Pacific and Central West Pacific regions were, quote, and I got this from NOAA, impacted severely by solar activity between 1830 Zulu and 1930 Zulu on 27 January due to the R3 solar flare radio blackout. 13 requests were received from ATC for overdue position reports. That means they lost 13 planes. They didn't know where they were. They couldn't talk to them. Several polar flights were altered due to the S3 radiation storm. You have these radiation storms and it just slams the high latitude regions because that's where the particles precipitate in. So as we keep getting more flights that travel over the poles, suddenly you can't talk to anybody anymore. And a major airline reported some of our polar flights, but not all, have reported HF comm outages over the past 3 nights. And I could go on. There's lots of this. So space weather affects ham bands and more. The FAA has to deal with this on a daily basis. And that's just a common storm. That's not really out of the ordinary. We get those, you know, easily 5 times a year. Maybe even more. Even in this week cycle we get them. Superstorms, how about this? This is March 16th, or 6th through 15th, 1989. We had an X-15 flare. The last slide was an X2. This is an X-15. This was followed by a CME. Weather satellites lost images for hours. The TDRS-1 comm satellite, that's for the Air Force, had over 250 anomalies. So now we're having problems in space. The satellites themselves, the health and safety of them are in trouble. Space Shuttle Discovery fuel sensor failed. Radio Free Europe was disrupted, and they thought it was a Soviet jam event. On top of that, the Hydro-Quebec power grid went down, and the James Bay network, you can actually see this black right here, that was down, and then the Hydro-Quebec is up in Canada. It caused this Toronto stock market to close because it was down for 9 hours. It melted transformers, if you can see that. These are power transformers. We saw aurora displays clear down easily as far as Texas and Florida. This is the DoD weather satellite, and the aurora is so bright it completely saturated the satellite. It's not even meant to see aurora. Many of the examples of solar storms in space, there's many more. There's the Telstar, there's Anik 1 and 2, there's the Halloween events of 2003. I could go on, and I'm not even mentioning the Carrington event. And the Carrington event was easily 3 times as bigger than this. So I'm not going to scare you with the super storms. But these do happen about once every 25 years or so. So the modern era of space weather. Well, space weather prediction centers were developed mainly as a response to these superstorms. And models we have models that predict solar fields now, they have CME transit, they have magnetic fields, they have, as you saw, HF radio, they have aurora propagation, aurora prediction, and all sorts of stuff. You can get solar storm alerts, you can get FAA alerts, and we have space and ground telescopes for monitoring of the sun, even on the back side of the sun, so we know what's coming around. And we have Spaceship Earth network, so we think the problem's solved, right? Well, maybe not. This is, if you notice the date, I don't know if you can see that date, May 13th. This is just a few days ago. This is a difference image of the sun. We use difference images, basically subtracting one image successively from the other, to be able to see what changes. The black is indicating what changes, and it oftentimes is a really good indicator to let you know if something left the sun. So just a couple days ago, we had this. Do you see this huge loop? Right? That is a coronal mass ejection, and that has left the sun, and it is coming, maybe, partially toward us. See if I can play this here. Come on. Okay, so that was the sun, the solar view. So here is Enlil. Anybody who's seen my models or my videos knows this. The top panel's density, the bottom panel's velocity. You can see one solar storm coming out off to the west. Here's that second little guy. See him right there? So we have a potentially grazing blow from this solar storm. You go to the next, whoops, don't do that. Go to the next one, okay. We have a grazing blow from this solar storm potentially on the 17th. It looked awful big. Then if I showed you coronagraph images, there is something that we call a halo, which means it's Earth directed. But the models don't really show that. NOAA has issued a G1 watch for storming to begin May 17th. But on top of not knowing the size and extent of this stuff, we also don't know the magnetic field configuration. Remember, the magnets have to click. If you turn one over and they repel, there's no solar storm. So will this storm? I don't know, right? But, and especially for glancing blows like this one, it's really hard to tell whether this model is correct or not. But I'll tell you this much. Amateur radio operators will be among the first to know on May 17th, because you guys are the real space weather field reporters. So, some parting thoughts. Amateur radio is affected by space weather every day. It's just like the weather in your own backyard. It's just a little further up. And there are a lot of misconceptions that exist. I mean, look at this to the left here. say this. I mean, you guys know now. This is the BBC, right? Really good news, right? Really on it. A solar flare races towards Earth. If it does, it already hit. 8 minutes, people. It's a CME, but these meteorologists have no idea what they're talking about. This was the September 12th storm. Now, this is when we actually had aurora down in as far south as Brittany, France. It's really hard to get your aurora in Europe because the magnetic field is tilted away. We're lucky in America because we actually have the aurora cap, the auroral cap kind of tilted towards us. But this storm had a very little impact. And the reason why was because instead of the magnets clicking, they repelled. And the sad thing was that a couple of these broadcasts were put out the day after we as scientists already knew that there was going to be nothing. And I had all my Twitter followers, I was lamenting with them that there's thousands of people because of these broadcasts that are out looking up at the sky. And I couldn't get to them and say, guys, don't bother. And these guys, as good as they are at terrestrial weather, they don't have the skill set to be able to do space weather. It's not the same. But weather is where this belongs. So we need credentialed meteorologists that are made to do this stuff because space weather broadcasts, it can be presented in a similar fashion as the terrestrial weather broadcasts and can be made understandable. And so I'm hoping that you guys will help be the inquisitive public and help us raise awareness and bring space weather more into the general public sense. And please come visit me on Space Weather TV, on Ham Nation, tweet me on Twitter. I am very responsive, and you can also email me at spaceweatherwoman@gmail.com. Thanks for your attention. Sorry, I probably went way over.
All right, very good.
Thank you, Tamitha. If you have questions, Tamitha will be down in the Crown Plaza this evening on the second floor in the Contest Super Suite. So you can visit her there. And thanks again, Tim.
Kind of toward the top of your collar.
Okay.
So we're done with this.
Good enough?
Okay, so we have one more phenomenal presentation to go.
No problem.
And this is...
But you got to plug this in.
Go ahead.
All right. Jeez.
This presentation has been one that I've gotten more questions about since it was announced. And do keep track on Tower Talk, the Tower Talk Reflector, which is where I post the activities related to this forum. There will be copies of the slides that you saw here.
Where'd the mouse go here,
posted
Jim?
on my website in a few weeks, so you can look for that. And we'll get going here with our last presentation of the afternoon. Again, thanks for coming. This is the 2015 version of the Antenna Forum.
So how do we get up here now? Oh, we're up here? It's a miracle.
You're only up.
I want to, yeah, how do I see this here? No, I think you're right. It's probably some sort of a function key thing. Me neither. Oh, wait, hold on, function.
Title of our next talk is Quadcopter Drone in the Assisting Real-World Antenna Pattern Measurements. Please welcome Greg Orty, W8WWB.
Thank you very much, everybody. Thanks, Tim. Thanks for the nice introduction. Hi to everyone out there. Hi to everyone on the internet. All right, let's get going here. You know, I was just thinking about it. We've been to the sun, 93 million miles away. We've been to the Earth. We've been to the largest antenna, right, 1,000 feet across. And now, folks, we're going to my backyard. Okay, so Tim Next time you may want to think about the other order on this, okay? I'm just saying. All right, let's get going here. Why should we want to measure antenna patterns? Do we trust antenna theory? Of course we do. Do we trust antenna modeling? Yes. So why? To me, it comes down to double checking our installation, and periodic maintenance is something not like it used to be. And of course, in some cases, we want to investigate unexpected antenna interactions. For example, is a nearby tower really acting like a parasitic element to an actual vertical antenna? I like to sometimes call these happy accidents, although oftentimes it's a happy non-accident as often as it is an accident, where you just might say, I have a vertical and it should be omnidirectional, but boy, it really seems to radiate very well in this one direction. Maybe that's something we can check into with this. And of course, there's always the mythical water tower, right? Is this water tower doing something to our signals? And of course, right now at this point in time, did I mention playing with drones, which is a lot of fun. Okay, let's talk about drones a little bit. They've frequently been in the news over the last few years, both for good and bad reasons. I think I heard about them twice yesterday, right? Some joker was flying one or tried to too close to the White House. I don't know what they're thinking when they do that. And I saw another unit advertised or came out with the Lily. It's a small drone that you actually like throw in the air and it starts to fly and it can follow you around, coming out next February. So I mean, there's a lot of things happening with drones. A helicopter-style drone, I think formerly we would say a rotary wing aircraft as opposed to fixed wing, with 4 propellers is called a quadcopter. And I guess I sort of like quadcopter better. Drone to me sounds like some military thing out to kill people, but a lot of people seem to like drones. Pardon me? What was that? Okay, of course you don't have to have just 4 propellers. You can have more than that, 5, 6, 8, I've seen all of those. Those are higher cost systems. I believe they can be more reliable. I think if you have more than 4 propellers and the right software and hardware, you can set it up so if one propeller fails, the quadcopters or the drone still stays in the air, which of course is quite nice versus falling to the ground. Of course, we're part of an exploding toy hobby professional market, constant stream of new products, new features, capabilities. A lot of it is about, of course, aerial photography and fun flying, I would call it, but I think that's true for radio-controlled models over the last 50 years. I bet if I asked for a show of hands, a lot of us have played with radio-controlled models. It seems to be a synergism with that in ham radio. They're a lot of fun. There's a lot of new applications taking off all the time, and of course, YouTube and other websites have endless information about this. DJI is a leading manufacturer. They're based in China. They're up to 3,000 people in about 10 years. They make hobby, commercial, and professional products. I think they're so ubiquitous that their images are often used as generic drone examples. They've been releasing products at about a rate of at least once a year. The first one that I think had some stir about it was the Phantom 1 that was released less than 2.5 years ago, January 7th of 2013. That's the guy on the left. And of course, with that, if you were like me and many other people, you bought the Phantom, which is the quadcopter here in the white plastic and red, but then on the same day you ordered this from somebody, you made another order on the internet to get your GoPro Hero camera, okay? Because that just was inserted into a mount on the bottom, and you could adjust the little thumb screw to pick the angle, and you would turn the camera on, send the quadcopter up, and hey, you're shooting video or taking stills every so many seconds. Lots of folks did that. Some of my first videos on YouTube at Tim's station, K3LR, used that exact setup. And the signature of it, if you don't edit away the video, is of course you start off in the grass, right? Because that's where you turn on the GoPro when it's down on the ground and it takes off and you go from there. They introduced the Phantom 2 line about a year later, and I think the top of that, the one I used for some of the videos and that we'll be seeing here, is called the Phantom 2 Vision Plus. And that takes the first unit and adds to it a couple big important differences. To the camera, now notice it's their own brand of camera here, not the GoPro brand, and I think some people who are real finicky about video, have said that the GoPro is a little bit higher quality, but they're still both very good HD quality cameras with, like 12 megapixel imagers. So this is not cheap video or stills. So the camera's fine, but it is their own. But the main thing is in between the camera and the body of the quadcopter is a gimbal, a 3-axis gimbal. And that's a gyroscopic-based stabilizer that keeps the camera level even though the quadcopter is moving around and trying to maintain its position. Okay, and that's really important for video. Without that, getting good stable video or pictures is very tough. Okay, these things are really easy to fly. I took mine out of the box, charged up the battery. Of course, I'm expecting to go up in the air and then it takes off into a tree or something else very bad happens, and of course it's the opposite. You take off, you go up 10 feet, you let go of the joysticks, and it just hovers there. And you don't have to do anything about it. Why are these so easy to fly? Well, they have a GPS built in, magnetic compass, what they call an IMU, inertial measurement unit, which is really an accelerometer and a gyro, barometric altimeter. All that goes into a 32-bit CPU, sort of the real-time flight controller. As I said, if you let go of the controls at any point, it just stops and hovers in place. So it's very nice. They've tried to make these things sort of idiot-proof, if you will. They have a lot of fail-safe features that are generally called like return to home. So if you lose signal from the transmitter to the quadcopter, or other things happen, the battery runs too low and you haven't already landed, it returns to home automatically, because of course with GPS it knows where it took off from, and that's the home point. They have a manual mode where you can dispense with all this GPS-based control and somehow fly it more manually. I've never tried it. I don't want to try it. I don't know what it does. I get scared always and make sure the switch is in the right position, because that sounds like skill, and I don't have that about it. These things do weigh about 3 pounds flying weight with the battery. So of course, always be thinking about what it can fall on. And is that going to cause a problem with your neighbors? The flight time is around 10 to 20 minutes. It depends. That Phantom 1 was probably under 10 minutes. The Phantom 2, they talk about like 23 minutes. I tend to measure 18 minutes quite reliably. And that's for shooting video purposes, and that it's not too bad. If you need more time, of course, just go buy more batteries and charge them up. And needless to say, we're in the middle of all of these hot topics with safety, privacy, and regulation. And who knows where that's all going to work out, but for now it's sort of the Wild West. With the Phantom 2 series, they added in telemetry back down to the ground and what's called FPV, which stands for first person view. And that means that you're looking at something as if you were on the vehicle looking out the front window, the first person view of it. And so that's quite nice, especially for flying it. With the Phantom 1, if you wanted to do that sort of stuff, you could put together sort of an a la carte combination of third-party pieces, but it was kind of kludgy at best. The interface on the ground is a smartphone or tablet, and I think the thinking is everybody's got one, if not 2 or 3. And I think that's true. My only gripe is that I find these things to have very poor visibility in bright daylight. Does anybody have a particular smartphone or tablet they think is wonderfully viewable in bright daylight? I don't hear a lot of things going on out there. This to me is sort of the problem. And in fact, if you look at the 4th flyby video from K3LR, you'll see just me for a few seconds with a red bath towel over my head, because I need to get rid of the sun and just look at my screen. Here in the bottom left is sort of what you have, the quadcopter, and then next to it the transmitter with the 2 joysticks and a couple other switches. And then lashed onto it in a clamp, there's your smartphone, okay? And then what the smartphone is seeing, or a tablet, is the view here on the lower right, which shows, of course, what the camera's seeing in real time. This one isn't really off the ground very high yet, so it's a sidewalk and whatever else is in there. But the other telemetry is around it, right? So we have the distance. It's not really gone anywhere, 0 feet, altitude 4.4 feet, speed 0 miles an hour. And then over here you can control taking stills, taking videos, changing the settings. You can see the number of GPS satellites. You like to have more than 6 satellites, or things may be more difficult. The batteries on the quadcopter. So there's a lot of information. It's really good stuff. They just released the Phantom 3 like in the last few weeks. It's about the same price as the Phantom 2 Vision Plus. It's got a 4K Ultra HD camera on the Pro model, which of course is 4 times the pixel resolution of normal HD. They claim that the FP video can go 1.2 miles and is full high def, which is quite nice. It even advertises downward pointing radar. You know, the one problem with trying to fly these is flying them indoors, okay, because GPS and that isn't quite as reliable. Apparently there's a market for flying these indoors, go figure. And so to make that possible, they put in this radar that's sort of like the old Polaroid cameras that would have the ultrasonic sensor to see how many feet away we are. They do a similar thing, and now this allows them to fly nice and level inside, I would assume, over normal floors. Larger, heavier, more payload capacity. The interesting thing I noted is they advertised this software development kit. So now you can write your own apps that get into communicating with the quadcopter and getting the telemetry and location and controlling it. So for our sort of purposes, that I think is quite exciting. And then here's their controller down here showing a bigger tablet. Okay, so how cool is the video? I've got 2 video clips in this presentation that I hope we're going to play now here. Everybody who sees them still thinks they're cool, so we'll see if that's true. Ooh, a little music too. Now, there's a couple stations here. Here's my little part of the world. This is starting off slowly. Here's my 160-meter vertical, which is actually a aluminum tower with a whippet top. That's right, and it's actually top loaded. There's 3 wires that are kind of hard to see. Whip around here. There's my neighbors. Hi, neighbors. The gimbal also includes a tilt feature, right? So you can tilt down under control from the ground, tilt back up again, which is a lot of fun for highlighting things. Now this antenna that we're pointing at next here is a 40 and 80 meter 6-element vertical array. Okay, so there are 6 verticals in it. Each one is a 80-40 meter trap vertical, and the control box is in the center. What you doing? Okay, little adjustment here. That's the very center of it. We'll talk about this antenna again. That's the only reason I'm calling it out so much. Here's my little 60-foot US tower, crank-up tower. Probably other folks have something very similar. This is kind of fun, just climbing up the side of it. I should mention these 2 videos I uploaded to YouTube the other day, so if there's anything about them you want to see again, they're on YouTube. Just look for my call sign. You'll find my channel. Here's a little 80-meter broadband inverted V antenna slung off the top. There are 3 wires associated with it. Okay, my Yagi on top is a Sommer, S-O-M-M-E-R, Yagi. This would be the XP507, 20 through 6 meters with 1 feed. And if you notice, there's something wrong with it. And back, oh boy, 2-3 years ago, and this will be the test subject for some of the upcoming measurements, half of the 17-meter driven element cracked. And then we'll get close enough, I think you can actually see the aluminum cracked. It's not like a clamp gave way or anything, which I find a little bit unusual. There's my Yaesu rotator and a little rotator cage. Little quadcopter shadow there. Yeah, so here's where it cracked, and of course on the far end there's a plastic spacer designed to keep the elements from running into each other in the wind. That's all that's holding it up, okay? So, you know, these are hopefully a bit more artistic and impressive. This is my neighbor Tom, K8AZ, lives about a half mile from me as the crow flies. This is a 4-element 40-meter OWA Yagi, full size, up about 150 feet. We were deliberately taking these near sunset, trying to hopefully get some dramatic lighting, so you better think it's dramatic. This is all for you. Spared no expense. That's why the lighting is as it is, because the sun's, of course, near the horizon. Two of Tom's towers. He has a 4-tower station. Those of you that are contesters, I'm sure know K8AZ. I don't need to say any more. And for the most part, this is very easy flying. I think the only challenge to it is, of course, I know there's guy lines around and maybe dipoles or other things. So of course I'm always paranoid, what am I going to run into? But other than that, you know, there's no skill involved in doing this. And here's a little bit of video from Tim's station, K3LR. This is starting at the top of the 40-meter tower that has 3 40-meter Yagis, very similar to the one at Tom's. There's more antennas on that tower than just, of course, 40-meter Yagis, but it's sort of called the 40-meter tower. If you notice on the video too, especially at Tim's station, there was some undulation in the video, a little bit of sort of distortion. That I think is generally called by the folks who do this a lot jello. And it really starts with the quadcopter vibration, making it all the way back through to the camera. Hopefully there's enough mounting and the gimbal to isolate it, but in some cases, depending upon the conditions, that still comes through. Okay, we all know that the traditional way to measure an antenna pattern is to use an antenna test range. These can be large, acres or miles, expensive facilities, oftentimes only available to the military or commercial folks. Here's a picture I ripped off of a Motorola test range. They've got, I assume an antenna can go over here. Here's one part of the range that has the ground reflection range. Here's an elevated tower, 300 feet elevated range. One of the big issues that, as part of this, is whether or not you're interested in including the effective ground or excluding the effective ground. And of course, you know, you need to think about that and make sure you're doing the right thing. To me, while the exploration of free space antenna patterns is valued, what I think is exciting about using drones is that every station can, in effect, be an antenna test range. And of course, it's based upon the actual antennas there and their actual conditions. And if we can measure that combination, that's the reality we have to work with. This should sound pretty easy, I hope. The concepts are straightforward. Connect an appropriate antenna and radio to the drone, fly the drone to an appropriate point in terms of azimuth and elevation in space around the AUT, antenna under test. Either rotate the AUT with a fixed position drone, or if it's something like an array that's electrically steerable, not mechanically, move the drone around the AUT. Okay, capture the signal level data, plot the pattern. Hey, sounds pretty good. Can it really be this easy? Conceptually, yes, but of course the devil is always in the details. I thought of at least these problems. There may be more. Things like how do we record and plot data? What sort of drone radio do we use? I don't mean the radio, of course, to control the drone. I mean our radio that's going along for the lovely journey. What sort of drone antenna? And then, of course, what about this near field and far field stuff? Because we're not that far away. What about polarization? What about ground? One thing that I think is not a problem is worrying too much in terms of results about which way we're transmitting. Are we going from the drone to the antenna under test or the other way around? And that's because antennas largely are reciprocal, meaning the transmit and receive patterns and response are the same. So if we measure either way, we know both. In terms of recording and plotting data, I used a program that, in fact, I wrote a bunch of years ago. It's been about 15 years, called S-meter Lite, and it's a free program on the internet. It just repeatedly reads the S-meter from the radio about 10 to 20 times a second, assuming the radio is one of the ones that includes that command in its remote control command set, plots a graph of the average data versus time, and then you can create a typical azimuth plot from that. And the accuracy is not too bad if you take the time to calibrate it. Here's an example. On the left, we have the main window of the program set up to be the dB scale. And so what you're not seeing here is my Yaesu rotator. So my friend Paul, intrepid Paul, out in the yard, has the quadcopter out and up to be, I think in this case, about a 15-degree takeoff angle on 15 meters, what we were doing. And he's in position. Of course, we're talking on the cell phones. This all needs to be automated. It's one big mess right now. But in any case, I get the rotator going. The particular rotator has an extra 90 degrees of rotation, like many do. So when I get to about 210 degrees, I hit the mark button. The rotator keeps going. The quadcopter's not moving. It's sending a signal. We're collecting it here. There's the rear of the antenna. There's effectively the side, there's the front of the antenna, and then when we get all the way back around to the same azimuth, I hit the mark button again, that's the second red line, collect a few more seconds of data. Of course, I may be slightly off in how I hit the mark button, so when you get into the second screen after hitting the antenna plot button, you can adjust the marks, kind of tweak it. I like to call it stitching it together so that you really have 360 degrees and not more or less. And then you get the pattern on the right. And of course, you could do this for the last 15 years with the program. It's not that new. But what would oftentimes happen for testing would be the other station would be a ham, 30 miles away, your good friend. And of course, that's quite indicative of typical signals. But is your friend available? What else is going on in the bands? Things like that. The drone radio, although in this case, right, we're picking that the direction of transmission is going to be from the drone to the ground because we're using S-meter like with our radio. That means we need a transmitter. And what's nice about going from the drone to the ground is that we have something like a receive-only antenna. We can measure that. If we went the other way, of course, receive-only antennas would be a little bit out of luck. We don't have to record data on the drone, but we do have to transmit enough energy that we can get through the couple hundred feet. And we need an antenna that's matched enough, efficient enough to help convey that power there. The radio antenna needs to be light enough to get up there. And of course, if we're transmitting, maybe we need a heavier battery. And that's, of course, working against us. For getting going this last spring and after winter, the first experiments were conducted with the Elecraft XG3 RF signal generator. Small little guy, very nice. It's relatively low cost, about 180 bucks. It's lightweight, about 4.3 ounces with a 9-volt battery. Covers all the HF, VHF bands, and you can even change the frequencies by programming it via USB from a PC. One thing we noticed that probably for the sane way to use this is that it's a 10-minute automatic shutoff I couldn't disable. So again, as part of the whole, can I say Chinese fire drill? Is that politically correct? It's part of this whole insanity of getting the measurements going. At some point, usually the last thing is to hit the XG3, because now 10 minutes, it's going to turn off. And if you're up in the air, you're just wasting something. Its maximum output power is 0 dBm, 1 milliwatt, which of course is about S9 plus 73 if you do the typical definition of S9. And it's quite rugged, I should say. Okay, can the Phantom 2 lift an XG3? The answer is yes. Here's my first test of that. I just had a simple piece of wire pulling it up. The Phantom 2 Vision Plus payload capacity is poorly defined. It's not like they say in a manual, you can't take off with more than so many ounces or grams. I think the reality is if you can take off, you've taken off. And if you're heavy, you're going to reduce your battery life. And that's pretty much it. Other than that, have a nice day. I have an opinion here. You know, there's been a lot in the news about people, Amazon, and other people delivering things by drone. My opinion is these folks are nuts. Because if you look at what's going on here and the cost per weight, and are you going to get it to your house, and what happens when 10 of these are on your street, you know, I just think there's a lot of wishful thinking. That's just me. Okay, the drone antenna. It's a major topic, perhaps the #1 challenge to getting this whole thing to work. You know, it can be tough to build any antenna, but now we want to build a light antenna, okay? Here's in fact where we might want to have one of those isotropic radiators you hear about, like DBI, signal gain compared to an isotropic radiator. Well, of course, they don't exist. It's a nice concept. My first choice was a vertical dipole hanging from the drone, and I just picked sort of 8 to 10 feet as being enough to radiate a decent signal without worrying about matching. So here are 2 examples that I had. They're both about 9-10 feet long. The left one has the XG3 in the center of the dipole. Okay, so there's about 5 feet of wire, the XG3, and then 5 more feet of wire with a bolt on the bottom, which is my only idea to try to make it hang straight. The one on the right was a bit more thought out, even though it looks kind of ugly. There, the antenna is number 24 magnet wire, fed in the center with a little piece of perf board with RG178 coax going down to the XG3, which is hanging from the bottom. Okay, so we have a longer pendulum arm, which should slow us down. And the other thing you see that looks to be sort of coiled around here is 60-pound fishing line, because of course my goal in all of this is not to drop the XG3 from hundreds of feet. Although I did manage to do that. That's coming up, don't leave. Each was under 2 ounces. Okay, so what's the difference between the two? Using that 40-meter vertical, an 80-meter too, but on 40 meters, vertical array, so the polarization matches, we sent up both of the antennas, one right after another, same day, same weather, so hopefully the wind and that's all the same. You would probably want to conduct the experiment 10 times and average it, but that's for scientists. Where's our scientist? Did she leave yet? Okay, well, I'm not one of those. But this was just one example of each. And what we found here was that by going to the bottom XG3 on the bottom trace, it was much more stable. Okay, the center loaded one, the center mounted one was up at the top, and of course this is with nothing moving, right? So this should be a flat line. We're trying to get a flat line. And of course, we're obviously not doing very well. And of course, what's interesting about this is that our goal in this is to measure our antennas, but now the antenna under test is the drone antenna, right? So, you know, we're already going sideways. Oops, we have some video of that. Where's my cursor here? Although it's very quick. So on the left is the XG3. In the middle, and you can see the bolt at the bottom, I hope. And then on the right is the other one, and I guess this is just a hand waving saying, no, the one on the right just looks more stable. But this is what you can do when you got a camera nearby, and this is about 150 feet over my house. Okay, polarization does matter. You do want to match the polarization between the drone antenna and your antenna under test. So I needed a horizontal antenna here to get to the Yagi. And for a horizontal dipole about 10 feet long, I used aluminum tubing from K&S. For those of you into hobbies and that, K&S tubing's out there. It's very light and telescoping. It's sort of the baby brother of what we use in our amateur antennas. So I created this little guy. I wonder if this is the first time this has been abused to carry a 9 or 10 foot dipole off a quadcopter, but blame me for that. The mounting of it was a little bit interesting. Ultimately, the XG3 was sort of at the bottom, pointing up so I could get to the buttons, some perf board. The quadcopter was really above it, all held together with rubber bands. Yeah, this kind of look. Now, when I was at the hobby store, I saw some carbon fiber tubes. Are any of you into carbon fiber yet for ham radio stuff? I mean, You know, sooner or later you figure it's got to have an application for antennas. Okay, near and far field. We could talk about this a long time. The point is that there are regions around an antenna that aren't what you expect them to be, and seeing as we talk to people in the far field, we want to measure in the far field. Things like easy neck or 4-neck 2 patterns represent the far field response. So we want to make sure we're doing that. To me, if you're at least 2 wavelengths away, that should be reasonable. But of course, we have a 2 antenna system here, right? So that sort of puts 4 wavelengths on the table. Polarization does matter. In theory, 2 antennas with a 90-degree difference in polarization will not transfer any energy, okay? Meaning that, for example, the vertical and horizontal electric fields, you're not going to send anything one to the other. But of course, in practice, especially at HF, skywave signals traveling over typical distances take enough twists and turns up there that that polarization purity is blurred and we can communicate. That's good. But in the drone case, 2 antennas pretty close together and in direct line of sight, that makes this much more important. Some programs like EasyNet will show you the horizontal and vertical polarization, and the green is horizontal. That's pretty much the identical thing as the total response. That's what we think of the horizontal Yagi doing. But the red one in the center is the vertical response, which interestingly enough has a null in the direct middle of it. But it's reduced, of course, in signal. And if you get the polarization wrong, here I was measuring a horizontal Yagi with the vertical drone antenna. Obviously, this looks like some sort of a bad haircut, okay? Okay, vertical polarization example. I mentioned my 60 or my 40 and 80 meter 6-element vertical. It steps through 6 different locations. At the top is the pattern based upon a model. In this case, you'd like to fly the drone around the antenna. Don't have that sophistication yet to fly via GPS. So instead, I left the drone in one place, and I stepped through the antenna counting 6 Mississippis, and I'm going to copyright and patent that, 6 Mississippis, to get us some time rotating around. And then, you know, model or measure that measurement then pattern plotted out here shows the thing at the bottom. So to the extent that we're looking at those 2, I think we can say we're sort of in the ballpark, right? I think that's reasonable. Boy, the dirt on ground. I thought that was clever, but in the interest of time, let's skip it. The bottom line is that ground reflections play an important part in the overall far field response. And my concern is that the drone may be close enough that we have to be careful we know what we're measuring. Okay, remember we saw the dangling 17-meter element? What difference did that make? Here's a 17-meter pattern. I would say not much. And of course, if you heard the phrase like Yagis want to work or antennas want to work where they can be damaged but yet still, you know, valiantly fight on, well, that seems to be true in this case. The SWR did go up, but that was it. In looking at the patterns, about the only thing I thought that broken element, and I should fix it this summer, influenced was 10 meters. And this was the 10-meter plot that has sort of some sort of a problem here in the back end of it. And what I realized was that that 17-meter half element is a little bit shorter than a full half wavelength on 10 meters. And it's floating, right? And that makes it very resonant. And it's off to one side of the antenna, right? It's not centered on the boom, it's all to one side. So the question is that influencing it? To know that, it'd be nice to measure this from a couple different angles and see how true that is. Of course, here's the uh-oh, right? There's good and bad reasons to crash these things. There have been a lot of, go check YouTube, a lot of people have had issues here. People have hypothecated radio interference, software bugs. But in any case, while making, oops, and of course, let's see here. I'm going to go to previous. Aha, I'm the only guy who went back a slide. While coming down from an elevation measurement at 300 feet, we had some sort of an incident, Houston, and we came down pretty hard, bounced on the grass, landed upside down, trashed all the propellers. The interesting thing is that XG3 on the bottom, if you notice in the bottom right picture, got jammed up into the camera and other things like that. And you know, it was a little bit of a problem there. But what about the elevation pattern of a Yagi? A typical Yagi, it's determined largely by the height above ground, right? Little to do with the number of elements. So if we go back to a 10-meter Yagi at 60 feet, about 2 wavelengths high, which is what mine is, this is the model, right? There's major lobes at 8, 26, 45 degrees or so with deep nulls between them. So the question is, can we see this with the drone, right? They seem mighty obvious and hard to miss. So, of course, we would like to fly a curved path over the antenna under test to keep a constant distance, but that's harder. But we can do the red path here, which is straight up and down. And that's what we did. And it was coming down from this that we sort of had the incident. But what we captured, though, in that one time was this response, which is to say that on the left is the modeled response, and on the right is what we got. And of course, I turned it 90 degrees. I'm trying to line them up together. It, kind of looks good to me, but I have some concerns of how valid this is, because of course, the drone antenna is moving up and down between 10 feet and 300 feet, which means it has its own interaction with ground, which is mixed in with the Yagi response, right? And this is almost looking as if we're just seeing the one antenna and not the other. So there's a lot of things to sort out. Okay, in interest of time here, and I notice we're very close, and in fact, Tim's about to give me the hook. There's some more conclusions. Thanks to Paul Hubbard, my good friend I work with, Tom Lee, Tim Duffy. There's one more video. Are we playing this now or skipping it for later? All right, gang, thank you very much. I think Tim will have some concluding remarks. This is truly another glamour reel, hopefully a bit more exciting. Thank you.
It's an incredible amount of work that Greg went through, and it is certainly Greg's hope and many of us here that you will get out and experiment with things like this and find ways to have
mini
fun,
drones myself. I was looking into the Phantom.
And,
so that was neat. I love your application. Great usage of that. It's a good application.
So for now, I say 73, and we'll see you back here next year.